What is a set? Is our topic today. We all have some naive understanding of what a set is, and the point is to talk about why that does not suffice for doing modern mathematics. The naive understanding of a set up until the early 20th century was that a set is just a collection of objects that you could define willy-nilly. Bertrand Russell pointed out that this flimsy definition, as natural as it is, leads to problems that are at the very foundations of not just set theory, but all of mathematics, ultimately all of logical thinking. So what's the problem here, and why is it so pervasive? Well, Russell said, if a set is just any old collection, then you can have sets of sets, and then, presumably, some sets would contain themselves, while others do not. For example, consider the set of all ideas. We'll call that set S1. Now, this set S1 is an idea, of course, so S1 would be an element of the set S1. Whereas if S2 is the set of all birds, then S2 is an idea, but it's certainly not a bird. So S2 is not an element of S2. So far, so good. Probably S2 is more typical as sets go. You would expect probably most sets should not contain themselves. So let's look at this set of sets which do not contain themselves, like the set of birds as an example. So this leads us to this set S, which is the collection of all sets which do not contain themselves as elements. Evidently, S2 is in here, S1 is not. From the previous slide are examples, so what else can you say about this new set S? For example, does S contain itself as an element? It's a simple yes-no question. So there should be two alternatives. If S is an element of S, this says that S is a set that does not contain itself. Well, that can't happen, right? On the other hand, if S does not contain itself, then this is exactly the property we need in order for S to be included in the set S. But again, this leads to a contradiction. So we're left with no way out here. The simple statement S being an element of S, this cannot be regarded as either a true or false statement, because either way you run into the same problem. It's an inconsistency. It's much more than a problem for set theory, because we use sets in mathematics all the time. It becomes a problem in all of mathematics. If we allowed this problem to persist, this inconsistency will bleed into mathematics, would propagate beyond. By the rules of proof and logic, we'd be able to prove every statement we like. We would get that 2 does equal 1, and black is white, and so on. In fact, every statement would be both true and false. Then you might as well pack it in and go down to the corner bar, right? But before I tell you how we resolve this issue, let me point out that Russell's paradox can be recast in many different forms. Here is one of those many forms of Russell's paradox that avoids the language of sets, substituting instead the language of verbal logic. Consider the statement which I'll call P, which is simply the statement that, quote, this statement is false. So I'll point out this statement refers to itself and its single assertion. The single assertion of P is that P itself is false. Now we ask, is this statement P true or false? Well, if P is true, then it says P is false. No, that can't happen. On the other hand, if P is false, then this says P is true. And that's, again, a contradiction. We are left, again, with no consistent verdict. So in the early 20th century, the experts tried to figure out an escape plan from this. Rather than describing how Russell resolved this by using his theory of types, let me tell you the approach which has become more or less the standard in 20th century mathematics. And for starters, we have to give up the idea that just any old collection can be called a set. not just any old string of letters or symbols can be called a statement. We need some rules that restrict the kinds of things that are sets or statements. Anything that's not allowed by these rules cannot be considered as true or false. It's just thrown out as nonsense. Similarly for sets. The collection of all ideas would hopefully not be a set, just like the collection of all sets, as we'll see, is not a set. The question is, what should these rules be? Choose wisely, because these rules will become the rules ultimately for doing mathematics. The trick is to come up with rules that are restrictive enough to hopefully eliminate the threat of inconsistency while still allowing enough freedom to define all the kinds of sets that you care about, to be able to develop whatever mathematics you want to do. So the trick is coming up with just the right balance. Now, I cannot take the time to list the rules for set theory that we came up with, but I'll give you just a very quick description. First, I should say the biggest problem that we're trying to avoid is this problem of self-reference, allowing a statement to refer to itself or for a set to refer to itself. The new rules should be designed to avoid such an obvious pitfall as that. But you need to go further than that because there are other kinds of inconsistencies that you also need to eliminate. Consider this example. We have now, instead of one statement, we have two statements, A and B. Statement A says that statement B is true. Statement B says that statement A is false. Neither statement refers to itself, but you still have a problem. Because if A is true, then B is true, then A is false. Problem. On the other hand, if A is false, then B is false, so A is true. And again, that's a problem. Here the paradox arises not from a single statement referring to itself. The problem arises from a pair of statements, and the danger is that within a broad scope of mathematical endeavor, there may be a paradox lurking, which is hard to see, because it emerges only by combining a very large number of statements together in a complicated way. There may be an inconsistency that's hard to spot because no one statement refers to itself. Even 2 or 3 statements at a time still look okay. It's only on a much larger scope of looking at large number of statements that the problem is lurking. This is the problem that we need to worry about. So when we say we're trying to avoid a paradox or a contradiction in mathematics, what we're trying to avoid is ultimately having any statement provably true and false at the same time. So what set of rules could possibly achieve such a goal? The traditional solution from early 20th century has been to build a set of rules for set theory, which can then be used as a foundation for the rest of mathematics. Why set theory? Well, it turns out sets are just pretty basic. We use them all the time in every area of mathematics. They're useful for building other things, so it's a natural place to start. So let's go back to the original form of Russell's paradox and try to eliminate the problem there at its root. As I've said, we want to be sure that a set cannot refer to itself. This is a necessary condition, but it's still just a start. Ruling out one bad thing doesn't really solve the problem, and it doesn't help anyway because ultimately what we would like is a list of do's rather than a list of don'ts. So the rules should be some kind of constructive process, like the rules of grammar for most languages. Rules tell you how to build sentences in most languages. Like you start with basic sentences and the rules tell you how to form a basic sentence, and then it tells you recursive processes for building up more complicated sentences out of the smaller ones. So you start with basic sentence like I eat, and then the rules tell you how to build something like I eat out on weekdays, and then on the weekend I prepare meals with my family while watching TV. So our rules of sets actually would start with the empty set and then allow things like taking unions and intersections and Cartesian products, etc., to build larger and larger sets. This is really what our axioms will tell us that you can do. But still, like the rules for logic, it's just a little tricky to come up with just the right rules. We need to not be too lax. That would allow inconsistencies to creep in. But if it's too restrictive, you won't be able to do all the kinds of mathematics you want because you can't build enough sets. So just to name the prominent choices of axiom systems for doing typical mathematics, they are ZF, which is Zermelo-Fraenkel axioms, or the Zermelo-Fraenkel axioms plus the so-called axiom of choice. So the Zermelo-Fraenkel axioms, there's a list of 9 axioms, more or less, although they've evolved a little bit over the years. And strictly speaking, there's not just 9 axioms, because some of these are actually axiom schema, which are templates for building longer lists of axioms. So there's a lot of axioms in there. And then Zermelo-Fraenkel plus the axiom of choice would be the alternative popular choice. One might say that Zermelo-Fraenkel plus choice allows you to do, let's say, 99% of everyday mathematics. I don't know. ZF maybe does about 80 to 90% of that. Of course, it's silly to try to attach percentages here. Actually, if you do finite mathematics, then you can probably just use ZF. And for analysis, you're more likely to be using axiom of choice on a pretty much daily basis, but depends. So I'll try to talk about when it is that we are really using the axiom of choice, when we need it. How did we do here with achieving our original goal, which was to eliminate inconsistency? Do these axiom systems do the job? Do they eliminate inconsistency? Well, we've been using these axiom systems for about 100 years, and nobody has found an inconsistency yet. So, most mathematicians today would say we probably solved the problem, but nobody actually knows, and you cannot actually prove. We know that you cannot prove that these axiom systems are consistent, at least not within the axiom systems themselves. You'd have to pick some stronger axiom system to prove the consistency of ZF or ZFC. But at least one mathematician, one prominent mathematician, has voiced the opinion that these axiom systems probably are not consistent. So the late Vladimir Voevodsky, a Fields medalist, publicly expressed this opinion, that it's not consistent. He doesn't think it is. We just really don't know. We hope that they're consistent. But some mathematicians, let me point out, prefer to avoid the axiom of choice. And this is simply a matter of personal preference. The thing to realize here is different kinds of mathematics use different axiom systems, and no one choice of axiom system is more correct than another. So to repeat a metaphor used in an earlier video, it's not as though basketball is more correct than baseball. They're just games. And what we do care about in mathematics, we want to do mathematics that is beautiful, interesting, consistent, and useful, right? And the point is, if ZF is consistent, then so is ZFC. If ZFC is consistent, then so is ZF. And that much, at least we know. Beyond that, it's just a personal preference, what kind of mathematics you're into. As far as the distinction for whether or not you want to use the axiom of choice, it's customary when announcing new mathematics, new proofs, to acknowledge when you used the axiom of choice, when you found it necessary to do that. Zermelo-Fraenkel axioms, pretty much, you can just take without worrying about it because they're standard throughout mathematics, pretty much. So anytime you want to use something, you might even ask to use something stronger than ZFC, and then you definitely need to acknowledge it. Or some people prefer to use something weaker than ZF or ZFC, and then they'll explain that. So what is this axiom of choice that causes some mathematicians to lift up their eyebrows at it? Here's the statement. So suppose C is a collection of non-empty sets. It's really a set of sets, and I call it a collection of sets just to clarify the hierarchical distinction. The axiom of choice says that you can choose a representative from each of the sets in your collection to form a new set T, consisting of those representatives. Now, the sets in your collection could be disjoint, but it's not necessary That's the case we mostly care about, is when the sets are disjoint. You can imagine here, without loss of generality, that the sets in your collection are disjoint, and you're picking a representative from each one. For example, define an equivalence relation on the real numbers as follows. Two real numbers a and b are equivalent if they differ by an integer. So in other words, they have the same fractional part. So 1.37 is equivalent to 5.37. Think of this as the real numbers mod 1, or in other words, the real numbers mod the integers. Take a representative from each equivalence class. Well, that's not hard. You could take the set T to be the interval 0, 1, including 0 but not 1. And then every real number is equivalent to exactly one element of T. Which one? Just take the fractional part, and that tells you which element of T. You did not need the axiom of choice here. The other axioms suffice to be able to describe this process. You get the set of representatives. You get a process for finding which representative it is in T by using the power of the other axioms. And the point is here that the set T could be described in a rather explicit way. That's pretty much what you need to say to convince people that the axiom of choice was not needed. But here is a variant which is more difficult. Take an equivalence relation on the reals, where two real numbers are equivalent if their difference is rational. So for example, 5 is equivalent to 11, but 5 is not equivalent to pi. Here, instead, we have the real numbers mod the rationals. Once again, we want to be able to take an element from each equivalence class to form a set of representatives T. But what could such a set of representatives be? And the problem is really that there's too much freedom for constructing such a set. You could pick any one rational to be in this set, only one. You could take 0 to be in your set. You could take square root of 2 to be in your set, and pi is in your set T. And you can keep going, picking more and more, but having chosen 0, you cannot then take any more rationals. Having chosen square root of 2, you cannot take a rational number plus root 2. You cannot include 1 plus root 2. You cannot take any rational number plus pi if you've already chosen pi to be in your set. But you still have an awful lot of choices to come up with the set T. It would be easy if there were a finite number of choices or if you had an explicit formula, but you don't have that. You do have the axiom of choice. And either the axiom of choice or something equivalent to that is really the only way you can say that there is such a set T. The other axioms of Zermelo-Fraenkel are not strong enough to do it. Here is a somewhat more graphic example of where, again, you need the axiom of choice. We ask for a function, f, from the reals to the reals, satisfying these two properties. First of all, f should be additive in the sense that f of a plus b should equal f of a plus f of b for all a and b. Secondly, you want to require a couple specific values. F of 1 is 1, and f of square root of 2 is 0. Now I want you to stop and think about this. Pause the video. Think about what kind of function can satisfy these conditions. It may occur to you that you can satisfy most of this with a simple function. F of x equals x will satisfy the first condition and part of the second as well. But then it won't satisfy the last condition. Also, it's easy to find a function defined not on all the reals, but just on the subfield q of root 2, the subfield I mentioned in my first video. So q of root 2 is all the numbers of the form rational plus rational times root 2. Because there you could say f of a plus b root 2 is a for any rational numbers a and b. So this will define the function on a subfield. Now the question is how to extend this to all of the reals. And by the way, you cannot just make it 0 on the rest of the reals. That won't work. It won't satisfy the conditions. Because it would say that, for example, f of root 3 would be 0, but f of 1 plus root 3 would be 0, and then you get a contradiction, because f of 1 is 1. So you have to be careful. But using the axiom of choice, it's possible to go past cube root 2 and extend it all the way up to the reals. You want to talk with me about this problem, come to me and we can talk about it. But what I will say here is that whatever function you choose, from a graphical perspective, the graph of this is kind of bizarre. It's a dense subset of the xy plane. To graph it, the best you could do is shade the entire plane some kind of uniform shade of gray or something. So what I'm saying here is that the graph has points of f in every small region of the plane. So every small region of the plane has points of the graph. Now, the axiom of choice is such a natural idea. Here are a couple instances where you really expect to be able to use it, and you have to catch yourself because you say, oh, wait a minute, this requires the axiom of choice. Here's one. You want to say what it means for set A to have size less than or equal to the size of the set B. You could say that there's a one-to-one function from A to B, or you could say there's a function from B on to A. Now, those are not exactly equivalent unless you have the axiom of choice in general. Going one direction is not hard. So if you go in the forwards direction, if you have an injection from A to B, you can get a surjection from B to A without using the axiom of choice. But to go the other way, going from G to F, requires making choices for which value you're going to pick from the many available given by the function g. You think about this. This issue will come up in our next video on cardinality. Here's another place where you want to use the axiom of choice, and it's a temptation, and you can do it if you assume the axiom of choice, but it's a simple one. Let A be an infinite set. Then you want to pick a sequence, A1, A2, A3, and so on, a sequence of distinct elements in the set A. How hard is that? Well, you pick a first element, A1, and then you pick a different one, A2, a different one, A3, and so on and keep going. This is infinitely many choices. And sometimes you can write down an explicit formula for each AN, but in the general case, the only way you can say that such a sequence exists is the axiom of choice. So innocent. And in analysis, we want to be able to do this. So we will generally use the axiom of choice, but I'll try to tell you when we are doing that.